Welcome to our presentation. In this video, we present our work titled Semantically Guided Representation Learning for Action Anticipation, a collaboration between Sapienza University and the Technical University of Munich. The presentation is the following. We start with a short introduction, then we emphasize the main problem related to the task. Afterward, we proceed with the introduction of our framework. Then we illustrate its architecture. Afterward, we continue by explaining the concept of common communication space, and then we show some qualitative results and the conclusions. Action anticipation refers to the ability of intelligent systems to anticipate events before they occur based on previous observation and their understanding of the world. Such ability is important for unlocking real-world applications such as self-driving car. Formally, given a starting time tau s and an observation time tau o and an anticipation time tau a, the task of action anticipation involves predicting an action category for the action starting at time tau s tau seconds before it occurs and by observing a sequence of events lasting tau seconds. Approaches in action anticipation are mainly focused on two standard approaches. One, using action recognition methods, or two, using temporal modeling through LSTMs or causal transformers. Action anticipation is prone to future uncertainty, and actions are interconnected. As such, action recognition methods, efficient when the recognition of an isolated action is required, are not sufficient. On the other hand, while causal methods are good at modeling temporal dynamics, they fail to consider the unisolated nature of actions and their semantic connectivity plus their co-occurrences. Present as GEAR, a framework for action anticipation that uses prototypical learning and semantic interconnections to predict future actions based on their proximity in the latent space. Such proximity is built upon the relationship that exists between actions and their co-occurrences. Specifically, SGEAR uses two kinds of prototypes: vision prototypes and language prototypes. The former allows for capturing typical action patterns from spatial temporal point of view, while the latter serves as a semantic guide for organizing visual representations according to semantic relationships. Language representations of actions based on the properties of the language embeddings excel at modeling semantic relationships between actions based on their frequent co-occurrence in language. Gear is built from three main components: visual encoder, intermediate stage, and causal decoding. The visual encoder is a VIT that encodes video frames visually. The intermediate stage uses two novel blocks named prototypical attention and temporal context aggregation for enhancing actions with semantic information from prototypes and building causal temporal dependencies. More information is present on the main paper. The last stage, causal decoding, uses an autoregressive approach to predict the next state of the sequence of actions. The standout aspect of this framework is the training strategy guided by aligning visual and language representations through the creation of a common communication space while preserving the characteristic properties of the visual modality. Is a relative space where representations can be compared based on their geometric association with other action representations of the same modality. Specifically, given two representation space, the vision space and the language space defined by the prototypes of each modality, for an incoming visual action representation, we create this relative representation by comparing it against all action prototypes in the same space. Similarly, we do the same for the language action representations with language prototypes. Thus, the two actions can be compared based on their associations. To mimic the association from the language representation, which represents the semantic connectivity between actions, we minimize the distance between these two relative representations on this common communication space. An illustration of the effect of learning action prototypes with semantic alignment on the common communication space and without it. As we can see, with semantic alignment, SGEAR is able to encode semantic relationships into the visual space as inferred from the language encodings while preserving the visual characteristics. Action co-occurrence is critical for the task of action anticipation. Transferring semantic connectivity from one modality to another through common spaces permits to acquire new knowledge while preserving the characteristics of each modality. SGEAR lacks the ability to model the order of co-occurrence between actions.